And, wow, and as you heard, this meeting is being recorded and it is placed on our website. So for those who couldn't attend, can watch it there, or maybe you want to see it again, you just go into our website under the monthly meetings, and there'll be a link there. And today's featured speaker is Tom Field. You can almost touch the stars. So welcome, and again, live long and prosper, everyone. So introductions, this is the same slide that we showed last month, in that those in the orange, their terms are up this year. And so we said that there would be elections this month to elect new people for those positions in the orange. The ones in the white, they still either have another year in their terms or they are assigned administrators and managers. They're not elected like the Greco manager is assigned, has to be knowledgeable about the observatory and experience. So instead of elected, that position is assigned. Same way with the other ones, property and website. But the ones in orange are of concern. So last month's meeting, I put up this timeline, and this is the normal process that would have been expected without having in-process meetings, or in-person meetings, sorry. And I've noticed there is the 16th and the 19th. So the 16th was our last day for submitting nominations for those open positions, which down in the lower right is president, vice president, secretary, treasurer, and 2 board members. And the 19th is today. So, and then we all remembered that the meeting is on Thursday this time. We had some scheduling, juggling we had to do. And a list of nominees would be presented during the meeting and instructions on how to vote. So let's take a look on where we are right now. The results of the nominations, there were none. But remember now is that the leadership team considered this as a possibility during these unique times when we're not together, we're really not meeting people. We're just doing the online meetings. So it wasn't a surprise. So the leadership team made sure that we had a contingency plan. And we did that. We came up with that. All the current officers agreed, all those people in orange agreed that they, if needed, that they would remain in their positions for the 2021 year to maintain continuity and solid club operations, make sure things continue on until we can get back to normal operations. So per the club's command media, and by command media, whenever I say that, I mean our policy and procedures, our constitution and bylaws, those things that we have to comply and abide with. So per our command media, if there's no nominees, then the officers who volunteered to stay on are considered single nominees. So there is no voting, there is no other people that are vying for those positions. So they're called single nominees. And in this case, instead of the normal voting process, our command media requires an affirmation by club membership during the November general meeting. And our command media specifically says the November general meeting. So of course, even though things are turned upside down during this year, we are still sticking with the command media as much as is humanly possible. So all we need is a majority vote of the members who are present during today's meetings. Now, sorry, all of our guests, this is only for members. So maybe this will give you some incentive to join the club, throw in your $30 for next year. So we only need a simple majority. And what is the process? Well, here it is. So it's for EVAC members only. And do the following starting now, folks. This is happening now. This is during the meeting. Click on the chat button at the bottom of your screen. Now, sometimes it might be at the top of your screen, and you might have to jiggle your cursor around a little bit to get it to pull down. But it looks like that, little icon with a chat on it. Press that button, and then two options come up, either kind of everybody or all panelists. And click the all panelists. And what that does is that gets your vote just to us, and no one else can see it in case you're, want some anonymity to it. But either way, we're gonna see it. But check the all panelist options, and then just a yes or a no. You don't need to comment on it. This is an affirmation, so it's only yes or no. And you don't need to say, yes, it was a great idea and thanks and all of that, because that just kind of bottlenecks the process this evening. Just yes or no. And then you hit the enter to submit. So our Greco manager, Claude Haynes, he's monitoring and will follow the tally and report on the results in a few minutes, just prior to tonight's main presentation. So please do your information vote now, either yes or no. Yes means that you agree that the current officers will continue on in their current positions through next year to get us over this craziness that we're in the middle. No means that you don't agree. And if there's a majority no, then, well, we'll seriously have to consider what to do, because that means there'll be nobody in those positions. So we'll have to come up with some magical thing. But please vote and let us know, either yes or no. And the results will also be included in the December newsletter. So please do your affirmation vote now. I will go through a few slides slowly to give people time that they can do both, do some clicking and then look at our slide and listen to me. So I'll kind of do a little slower than usual. So our club news, there will not be a club holiday party in December. Oh, boo-hoo, huh? December's event will be a normal online general membership meeting, just like we're doing now. We'll have a meeting, and then we'll have a main presentation, and then that will be it. No parties. Hopefully you will have your own party while you're watching this event, but there will be no gathering, no party. All EVAC personnel contents, again, this is a broken record. They're canceled. All our meetings, star parties, outreach events, Greco, anything that involves the gathering, in-person events have been canceled until sometime in the future. We don't know when that is, especially with all the changes that are happening lately and the possibility of more changes coming in a few months. So we're just keep going month by month until we can get comfortable and the board can make a decision. Member presentations as usual. Hey guys, anyone interested in giving a 10-minute member presentation? By all means, please do that. The main presentations that are being done, these are done by industry professionals, top-notch people giving top-notch presentations. But remember now, our club has every level involved, and mostly by members who are just starting out. They're experimenting on their own, they're buying equipment, things like this. So those presentations are of value to everybody. So if maybe you're getting into astrophotography and you want to share the frustrations and the successes, by all means, a little 10-minute presentation could be a lot of value for some people who are in the same position. Or maybe you can get a presentation on what you've been doing during these lockdown times. Maybe you've been setting up your telescope in the backyard and inviting the family to come on out and touring the sky with them. Anything that normal lower level involvement people in our club would just be very happy to see that. So please, if you have any desire at all, give a member presentation, get a hold of me through the EVAC president link. And I can review the presentation. We can revise it, polish it up if you like. We can do a practice run before the meeting. So please, it's a fun thing to do. And plus you can say, yeah, I gave a presentation during an online Zoom meeting, right? Yeah. And remember, these monthly meetings will be recorded and a link provided on the EVAC website. Just go in, click on monthly meetings, find the date that the meeting was held, and there'll be a link posted there. I give Tom I don't know, a couple days or so to get it on there. But all the past online meetings are on there, are loaded on there.
Hey Gordon, we've got a ton of votes.
So, oh, good, great. Keep them coming in, guys. Keep Claude busy. We want to hear from you. We need your vote. You are the club.
We've got more than half of the attendees already, Gordon.
Oh, all right.
So,
yeah.
So we're
yeah. Hey, to celebrate the holidays and everyone supporting the EVAC online transition, on Saturday, the 5th of December at 10 a.m. Now it's 10 a.m. in the morning on a Saturday. This is way different than we normally have been doing, but this is a special event that Tom Mosden, our vice president, has set up for us. Is by Matteo Taka in the gravitational wave detection of Virgo and LIGA and upgrade plans. Now, gravitational waves have had a lot of publicity lately. They're discovering quite a few gravitational waves. And oh, by the way, it's gravitational wave, not gravity wave. Gravity wave is a meteorological thing. Gravitational wave is the astronomy thing. So it's a gravitational wave detection. So special, but thanks everybody. We're giving you this special additional top-rated presentation by one of our industry professionals.
Hey Gordon, let me just throw in that it's Saturday because he's presenting from Belgium.
Oh yeah.
And yeah, 7:30 just was going to be horrible for him, like 3 in the morning.
Yeah.
So
yeah, good. Thanks for saying that. Yep, that's why we picked that date. So our next EVAC meeting is Friday, 18th of December. We will be back to our usual third Friday schedule. So that's Friday, 18th of December, normal time, 7:30 p.m. And that meeting, which remember now takes the place of our party, is just basically a regular standard online meeting. And we'll have a main presentation as usual. Turbulence in the halos of galaxies. I don't even know what that means, but I bet after watching that presentation, we will know what that means. So our next step would be our main presentation by Mr. Tom Field. You can almost touch the stars. And I had mentioned this if you people that joined earlier. Get your votes in. Make your notes about the 5th of December, 10 a.m., and about our next meeting being on the 18th of December as usual. And get ready so that you're clear to concentrate on Tom Field's presentation, because I had the pleasure of sitting in on one of his presentations, and I highly suggest everyone get their duties done so they can concentrate on listening to Tom Field. So, Claude, how are we doing? I haven't looked as far as chat inputs.
We're doing fine. I have 39 yes and no no's, so I believe that's a majority.
Oh, yeah. But still, guys, we still have just a few more minutes, so please submit your votes. Uh, uh, just because it looks like we have a majority right now, please submit the vote. Also, just as practice. Now, that chat link could be at the bottom of the screen or it could be at the top of your screen. Generally, it's at the bottom, but it might be at the top. And if you kind of jiggle your mouse around at the top of your screen, it'll drop on down and you can click on that chat field. So very easy to do. Please, your votes count and it'll give you experience in case you have to do this on some other presentation you're watching. So we are 15 minutes into it. Claude, do you think we have a good tally, enough to make a decision?
I think so. If people keep voting, I'll monitor and I can adjust, and then I'll turn the final tally into Wayne for publication.
Okay. Okay. Good. Good. And so right now, as president of the club, I would I'm confident to conclude that the affirmation is yes, that we will continue with the offices being filled by the current officers through next year until the next election time, which would be next November. And guys, I think, that was a good decision because these times, we've changed, and without being able to sit down with a new officer positions and do a transition, it would be very, very difficult and might cause some issues. So guys, I have to agree, that's an overall good decision. And I think we can say that the affirmation is a yes, and we can close out the voting, the official voting. But still, keep them coming into Claude. There might be someone who, who's eating dinner or something. Okay, any comments? Tom Mazden, sorry.
No, I'm ready to introduce Tom Field.
And I just want to say, before Tom does that, is Tom Mazden is the one who sets up all of these online meetings and presentations. Just been doing a fantastic job. As president of the club, all I need to do is make sure all the other officers do their jobs. And my gosh, all the officers have been doing such a great job. My job is easy. So Tom, I will hand it over to you, Tom Mazden.
All right, thanks, Gordon. It's my pleasure to introduce our featured speaker today, Tom Field, who has been a contributing editor at Sky and Telescope magazine for the past 7 or more years. Author of RSpec software, which received Sky and Telescope's Hot Product Award in 2011. And Tom's a popular speaker, has spoken to hundreds of clubs via the web and in person at many conferences, including NEAF and EAF, the Imaging Conference, the Winter Star Party, Advanced Imaging Conference, and now the Distinguished EVAC Club to add to the feathers in his cap. All right, I'll get out of the way and let Tom take over.
Thanks, Tom. I appreciate it. And Gordon also. And as Gordon mentioned, there's so much that goes on behind the scenes with these meetings. And Tom and I was looking earlier today, he and I exchanged maybe a dozen or 2 dozen emails just in terms of, ironing out all the details. I've sat in on a lot of business meetings somewhat like this one over the years, and your club's really got it going on, a really nicely run process. And so I think that's one of the reasons the club is so successful. Your clear skies also probably have something to do with that also, shall I say. So let me share my screen here and pop that up. And if you can't see a prism there, let me know, but you should be able to. So I'm going to talk for about 45 minutes or so, maybe a little longer, and probably best to hold questions till the end. I don't know how it's set up. whether the people will be able to have audio or not. I think you probably need to click on the Q&A button at the bottom or top of your screen as you did for voting, and you can enter a question, and then we can go through those at the end. Other than that, let's just jump in a little bit. So how have we managed to discover so much about the universe when, you know, we haven't really even left home? We're just in such a local region. We've been imaging for what, 150 years or so. And, you know, when we look at an eclipse, we get a sense of depth. Instead of just two-dimensional images, you can see one thing's in front of the other. And if we wait a while, we can see things change. You can see up there, for example, in the upper right-hand corner, some stars going on and off, and there's others like that, or getting brighter and dimmer. And if we spread the colors out, we get aesthetically, this is very pretty, an as-if fifth dimension. And these gaps tell us a lot about stars. I like this just aesthetically, it's so gorgeous. Sometimes I try and figure out, well, where does this blue end and the green begin, you know? But these gaps reveal a lot about not only our star, but any object that we study. I'm not going to read these bullets, but I'm going to show some examples tonight of quite a few of these. They say about 70 or 80% of the astronomical research gets done using spectroscopy. So there's good reason to understand it. Even if you're not an imager, maybe you're even an armchair astronomer and you don't even go out and observe. I think what you'll find tonight is some of that foundation that will help you appreciate the stars in a newer, deeper way. Now, in the past, the next slide was for quite a few months was a bulleted list of about 10 key points that I wanted to communicate. I figured, why not just lay it out? Here's what I want you to go away with. But it was too many words. Nobody wants to see that many words. So I've got this new approach I'm trying. I've got this little dinging bell here. It actually has some heterodyning going on of some sort. Or vibrato. I may use that. I may just hold up this because there are some key points I'd like you to appreciate as we go through tonight. So first, just a little bit of science to get everybody more or less to the same level. Sir Isaac Newton discovered that we could bounce light or pass light through a grating, and we could split it into its component colors. Down here is an example. You can actually bounce light off a finely lined surface, even a DVD or CD, and get the component colors. And you can also pass it through a finely lined piece of glass called a diffraction grating, and that's what we'll be talking about tonight. Bunsen invented the Bunsen burner here to study a sample. He burnt it, he passed the light through a prism, and then he looked at the results. And he was a real pyromaniac, but the great thing about him is that he kept really good records, and those records served us in the decades and centuries going forward, as we'll see. Kirchhoff was a contemporary. We're not going to talk a lot about him. Just one quick thing on this slide here. There are two different types of spectra that you can get. One would be, it's got the Roy G. Biv rainbow in the background and its gaps. And this one down here you can see is a more or less dark background with bright lines called an emission spectrum. Whichever one of these you get, the cool thing is the lines are in the same position. And which one you get depends on things we won't talk about tonight that Kirchhoff did, and that is the temperature of the gases that the starlight is going through on its way to our eye and our sensors. So each element has its own unique fingerprint. So hydrogen here has this bright red line, but helium doesn't. So in fact, hydrogen is so commonly used, and of course is so common in the universe that it's nice to have a name to refer to its lines. The hydrogen bomber lines or hydrogen bomber series is what we use. And then we also have given the lines Greek letters like we give to the stars and constellations in terms of brightness order. This isn't in brightness, but this is from right to left. Alpha and beta, that's sort of I guess that's sort of a robin egg blue color. And this is a periodic table I created a few years ago. We sell it mostly to educators and schools and some amateurs who are really into it. I just want to show you a quick thing on this, and that is, there's our hydrogen, right? There's that red hydrogen alpha, and there's that robin egg blue line, and then the others stacked up here, getting closer and closer together. Excuse me while I do that. If we compare hydrogen to, say, helium, maybe this is a helium, maybe you filled a balloon at a florist shop, and now somehow you found a way to safely burn that helium. The lines are very different. That's the idea of fingerprints. We don't have to burn things anymore, fortunately. We have these gas tubes here, like you can see in my image. And these gas tubes, in fact, I'm going to just move a different screen over. This is a live camera view. We have this, I'll show it to you here. It's a camera looking at itself, or looking at a camera. This is a camera that we created for educators, astronomy, physics, and chemistry teachers to teach spectra. It's live. You can see there I am, diva that I am. And if I take this gas tube here and just plug it into the power supply and turn it on, there you can see the spectrum. There's a grating in the camera, and there's that red hydrogen alpha, and there's that robin egg blue, and some of the other lines over here. So this is the kind of thing Bunsen saw in like 1858. And when we started looking at stars, we saw similar lines. And that's how we turn that off and ditch that screen. That's what we're going to talk about tonight, is how that works. So far I've talked about old white men, right? I want to show some examples of other people who have accomplished a great deal in our field. Again, there's a ton of them. Annie Jump Cannon and her computers were denied time on the telescopes at Harvard because of their gender a little more than a century ago. So they studied these glass plates, photographic plates of spectra, and they were really good at it. They classified, hundreds of thousands. So they were fast at it, but more importantly, that gave them a lot of exposure to the data. And with their knowledge and deep understanding, they were able to come up with a star classification system that actually worked, unlike the predecessors. Priyamvada Nataraja, she's at Yale. She studies gravitational lensing with hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in late 1940s. A big proponent of the Hubble Space Telescope and helped make it happen. Elisa Quintana is a contemporary of ours, like some of the others I've shown here. She studies exoplanets, discovered some around red giants. And finally, Jedediah Eisler, she's at Dartmouth, and she studies hyperactive black holes. So we've made a little bit of progress. There's a lot more to go in terms of taking advantage, what an awful expression in this context, in empowering others besides the old white men. And there are, it's just enormous resource. This is a slide I put together this summer, and it was really a lot of fun to be surfing the web and looking at there's so many women who have done just amazing things out there. So what tonight I'm going to talk about mostly is this little grating here. It's called a star analyzer, and it's got some clear glass with some etched lines in it. Again, here's that ding for important point. One of the myths that I think we all come into this field with is it's going to be expensive to get started at this. $200, it's nothing. So there's lots of ways to mount a star analyzer. Just some examples here. Here, again, it's on the lens cap threads of a DSLR. We actually, I've got it here somewhere on my desk. So some adapters that screw into the lens cap threads or the T-ring of your DSLR so we can mount the grating. But other common examples, cooled, uncooled FITS camera, could be a color or mono video camera like this ZWO. You can mount inside a filter wheel. We'll talk a little bit more about that later. But I think the ding moment for that is that it's not a do-it-yourselfer kind of thing. It's not complex. You don't have to be grinding, and going out to machine shops and doing all that. Fortunately, because I don't have that skill, and many of us don't. There are opportunities to do that if you care to. You can mount your DSLR piggybacked on your telescope, take advantage of its tracking, as well as multitask and do two things at once. Okay, so there's a little about the history, the theory, and the equipment. What can we actually do? Check this slide out. Next one. So this star here, its light goes through the grating. Some of the light just goes straight through onto our sensor and is a star the way we're used to seeing it. But quite a bit of it gets split into this rainbow. Now here's the slide I was hyping. These are separate spectra of different stars captured by Torsten Hansen with just an 8-inch Newtonian and an imaging source video camera. Now the stars are in temperature order. So these are the hot B stars here going down to the type M stars down here. And one of those bullets early on I showed was we can tell star temperatures with their spectra. Look at the differences as we go from the hot stars down to the cooler stars. Just two quick examples here. One is these, well, those aren't even lines. That's like a forest, right? It's called a band. We don't see those on these hotter stars, just on these cool stars. Now, what that is on the cooler type M stars, right? These are the M stars over here we're looking at. The stars are relatively cooler. And so the gases on the outer shell of the star can contain more complex molecules that don't get instantly incinerated. In this case, it's titanium oxide. Now, truth be told, I don't know anything else about titanium oxide. You know, ding moment here, and that is you don't have to have a degree in astrophysics to do spectroscopy. You capture images like this, you read in some of the books, you get on the web, but you can go as deep as you want or not as deep. And I think that's been very attractive to me because, you know, I don't have a PhD in astrophysics or even an undergraduate degree in science. So the other example I wanted to show you here is these lines right here ran around 4800 in the, well, robin egg blue. So these are those hydrogen beta line. That's what we've named them. Notice that this line is darker, more prominent on this type A star, like Vega, for example. These lines up here on the hotter stars are dimmer. These lines on the cooler star are either dimmer or don't even exist. Well, clearly we can see temperature differences. So how do those come about? Just a brief bit of science here, again, to remind some of you, and that is the Bohr model of the atom has numbered shells in which electrons are going around. Some of you know all this and have taught it and probably teach it better than I am right now. And sometimes the electrons jump between shells, either up or down. When they jump from shell 2 to 4 or 4 to 2, they create this hydrogen beta line. So on these hotter stars, when the electrons are being pumped up, the stars are so hot, they don't stop at this shell 4. They keep going to 5 or beyond. So not as many electrons are making that transition. Similarly, on these cooler stars, not all the electrons get pumped up to level 2 or to 4. So there aren't as many to transition between those levels. So that's a clear way that we can see star temperatures differing. And again, the existence of lines and their thickness, so to speak, is the way professionals can identify star types, and so can amateurs. So that's what I want to show you. I love this example. You know, my wife is always urging me to dress for success, and I think this is about the best I can do. She assures me this isn't what she's talking about. But look, there's the hydrogen beta line, or alpha actually, right there. But, you know, here's the deal. You know, all of you at home, like me, I'm sure some of you have experienced what I'm about to describe yourselves, or maybe with your spouse or partner. And that is, if you look in this, we're all about colors in spectrum, right? If you look in this red area here, as you get down deeper, it's no longer that characteristic red. There's gray in there. And you know, the salon I normally go to isn't picking up. The salons I've been able to find open don't have appointments. And like I said, I'm sure some of you have gone through a similar experience. Anyway, let's go on and look at some of the other examples that we want to take into account here. You see that crosshairs there? So if I was to get time on a professional telescope, maybe somehow I get time on the Hubble, and I submit a paper that says, see that little bit of dimming there in the robin egg blue? We observed that on... That's not going to get accepted for a publishable paper, right? That's not science. For science, we have to be quantitative. And we do that by just plotting the intensity of this data in a graph that looks like this. So this graph here is intensity. So the starlight that went straight through the grating didn't get deflected. Let's see, that star is really bright and narrow, so this peak is really high, and this feature isn't very wide. Whereas this here, right, is really wide. There's not much light here. There's more here, and there's not much here. So it's dim, gets brighter, 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 dimmer, dimmer, dimmer. And look at this. That barely discernible dip in brightness there is very clear as an absorption feature or absorption line. So my story is I wanted to do some spectroscopy in 2009. I got a hold of a grating. I took my C8. I went outside, right outside the windows here. I'm 3 miles from downtown Seattle, Pike Place Market. One Saturday night in August, I went out. I actually used a Logitech webcam. I duct taped it to the barrel of an eyepiece that I had removed. And this is a frame from a video that I shot. I came in at midnight, Remind me not to eat dry crackers just before I give a talk as a quick appetizer to my dinner later tonight. So I came in at midnight. I had a neck ache. The blue jeans I was wearing, they were grass stained because I'm looking at Vega. It's overhead in August, right? So let me do a little more drinking here. Pardon me. Sunday morning, I went to create this graph and I couldn't. I downloaded the freeware that was out there. One wouldn't even install. It was DLL hell, if you know what that is. Another one, it kept crashing. The error messages were in French, as were half the screens. There was no manual. So what did I do? I gave up. I told my wife, this is a hobby. I'm supposed to be having fun, and I'm not. So I literally put the grading in the drawer and gave it up. But it kept bugging me. For the next couple of weeks, I kept thinking about it. So one day, midweek, I thought, Saturday, I'm going to write a program to create this graph. Sunday morning, it was done. And now, and this is literally that first image and that first graph. Now, 10 years later, 10 or 15,000 hours later, the software's, it's almost done. I hadn't intended to create a product. My wife keeps saying, would you finish it up so that we can have dinner at a decent hour? It's done. She used to say that. She doesn't need to anymore. So I think, and this is a ding moment also, one of the, it's sort of a wimpy ding, isn't it? One of the concerns that we all have when we come to using a new piece of equipment or new piece of software is, oh no, now I've got another piece of software to learn, pain in the neck. So I think that's, of course, that is a legitimate concern. Now, listen, I know it's after dinner for all of you. So if I give you a long software demo now, I'm going to lose you. It's sort of nice. It's a webinar, so you don't have your cameras on, because when that happens, all we see are the tops of people's heads and your mics are muted, so we won't hear you snoring. But I think it's important. Less than a dozen clicks I'm going to show you here just for a minute or two. I think it's important for you to see how we create these graphs and what they look like. So here's my software, and there's an image. It's actually a frozen frame from that first video I captured. And listen, ding moment here, I was not an astro imager. There are people here in your club, as you know, maybe you're one of them, who are really good at this stuff. You do not have to be a good imager for this. In fact, it's easier than normal imaging in some ways, because with normal imaging, we need dark skies, we spend a lot of time post-processing, getting the aesthetics and the levels all right. None of that do we do here. We don't want to mess with the photons after they hit our sensor. We want them, when we bring them into software, to just be pretty much the way they hit our camera. Now, we can stack images and do flat fields and darks and stuff, but I was not a big imager, and I found this pretty easy. So this is a static image. If it's a FITS camera, you'd capture it on your current FITS camera software. You can have the software, my software, automatically loaded into here. It could be a video. So all you do is bracket in the region that you want to study. And I like using color for outreach and webinars because it's more intuitive what's going on. Of course, mono is a little more sensitive and a little better scientifically. Bracket in the region you want to study. And now we have a big peak here for the star, and this data there with lots of dips, including a very deep one right there, is this data. There's some gaps there and a big one there. So now we're actually, have an intensity graph to do some science. The next thing that you might be saying, as I would in your shoes and did, is so what? What are all those dips? How do I know? Well, remember I mentioned that Bunsen had created a catalog of all the gas tubes he'd observed. Gas tubes, or not gas tubes, but gases that he'd burnt. Well, that catalog, or its great-great-great-great-grand catalog, is grandchild catalog, I guess I should say, is still in use today, and some of it's embedded in my software. So let's just click and bring up that catalog. We'll come down here to the hydrogen bomber lines. I'm going to tell the software by checking this box, show me in the graph where the absorption lines would be if this star had hydrogen gas affecting the light as it left it, Vega. And you can see that the lines, the reference lines where we're expecting dips, we're actually seeing them. So on a backyard telescope, first night out, webcams in the city, really amateur rookie observer, me, we're able to actually observe the impact of the hydrogen gas of that star as the light left the star in those dips. Really amazing, huh? So a couple of quick things to show you here. First of all, let me turn off that fill and just zoom in on this feature. Now I'm going to play, this is actually a frozen, a paused video. Let's actually start it playing. And you can see the star and the data is jumping around here, as is the graph. And you can see that feature is, really changing a lot as my seeing changes. Well, most of us are familiar with the fact that if we stack images, if we average them or combine them, we eliminate noise. So let's turn on stacking in the software. Normally you'd use a third-party stacking program, but on video I've built some in here. Let me turn that on. Watch that feature. We're playing it this video at 2 frames a second. So let's turn it on. 1 Mississippi, 2 Mississippi, 3 Mississippi. See how that feature just squares up, gets nice and symmetrical. This is the beauty of stacking. And that's sort of a fun thing to show. One last thing to mention, and that is spectroscopy is a great ding moment, great tool if you're doing outreach. Earlier, before the meeting started, I was talking to some of your board members about the outreach you do to schools. Now, for elementary kids, maybe there's not a lot to talk about on this screen. But for older students or out on the sidewalk in public, this can augment a visual telescope. This color and the movement that we see here is really attractive and interesting to people. And this gives you the chance to transition into a little bit of science talk. You'll be surprised, perhaps I was, in more affluent, better educated neighborhoods, a lot of the people will go, oh yeah, I saw that in Tyson's, was it the 3rd or 4th Cosmos? And somehow they know it, but this is a great screen. I've spent more time on it just now than I wanted to. But what I would like you to do as we leave it is just keep in your mind's eye, if you would, that view, right? It happens to be Vega, but the thing I want you to keep in mind are those reference lines that go all the way back to the days of Bunsen, showing us where the hydrogen bomber features, the hydrogen alpha, beta, gamma features would be, because we're going to look at some science that uses those in a couple of minutes. Here's a star party, for example, I was mentioning a moment ago. They're looking at a gas tube of some sort here, and then they transitioned into doing starlight. This is actually taken in France. You can see some of the French there. Here's a wide field DSLR view. You can see some stars. There's some gaps. There's some absorption features down here on this star. We can see some lumps, right? It's a lumpy spectrum. Again, these are emission lines. We saturated our pixels. We have a little bit of blooming going on. But let's look a little more detail at Wolf-Rayet star. So I have a confession to make to the group. When Janet Simpson sent this to me about 10 years ago, I couldn't remember what a Wolf-Rayet star was. Well, Wikipedia is our friend. Wikipedia tells us that a Wolf-Rayet star is a late-stage star, a massive star, maybe headed to being a supernova. It's got an intense stellar wind as it's dissipating some of its outer layers. It's an emission spectrum, so we have some bright regions. Let's look at them here. Carbon, carbon, carbon. Why would we be seeing carbon on a star? Well, of course, there are carbon stars some of us look at. But in this case, just a reminder, of course, that stars burn through the elements. And one of the steps is burning carbon. And we're actually seeing that spectroscopically. And you see in the caption there with just a DSLR, mechanical tracker, and 30 seconds of time. So this is probably the biggest ding moment for me. My experience has been, and those of you who image know this, when you get the data in hand, especially if it's your data, your whole relationship to it changes. Now, for a lot of us, it becomes something, well, why would there be carbon in this? And you go out and you read a little bit. Maybe you get bored and you don't read anymore. Maybe you continue to dive down or ask some friends who know more than you. And it sticks because you have this emotional relationship to the data. I found that happen for me. Now, listen, your data is your data. If you're an imager, you probably remember your first image of the moon. Mine was overexposed. It was blurry, but it was the most beautiful. I was showing it to my wife, my colleagues, my friends. So, but your data makes a difference in terms of how you relate and what you remember. So let's look at another emission object, the Ring Nebula. So there's its spectrum. You can see there's just two features there, two emission lines, hydrogen alpha and oxygen. That Roman numeral 3 just says it's been ionized. Some of the electrons have been pulled up. So most extended objects, non-point sources, with a slitless grading like this are pretty uninteresting because there's lots of data and it all overwrites each other. Notice if these two happen to be adjacent to each other, then this green would merge with the red and it would just be a smudge. It wouldn't be anything interesting. So as I knock my table off or my camera off the table there, let's look at another emission object, but this time let's use a higher resolution slit device so that you see the difference. So these devices are, if I can stick on that screen, these devices you can see are like an order of magnitude more expensive. And they're a lot harder to use because now you're acquiring your target and guiding on like a 20 micron slit. It's a steep learning curve and almost nobody, like 1 in 100, starts out with these devices. There's a lot to be learned by going through the learning curve with just a low resolution grading like this. That's what most people do. So here's another emission object. It's an extended object, and we're looking at it with a slit spectrometer. So even though it's extended, we can see some nice, really tight, narrow peaks. We see some nitrogen. There's hydrogen alpha. There's that Roman numeral 3 on oxygen, so it's ionized. So sometimes when I'm doing a meeting and instead of a webinar, it's just a Zoom sort of conference call, I'll ask members to describe their first M42 experience. I'm fishing for a story like the one I'm about to tell. It's fun when you can remember back before you understood something or knew something. So in the early 1990s, I wanted to do astronomy. Shoemaker-Levy 9 I'd read about in some magazine. I went to a star party for the Denver Astronomical Society, urban first quarter star party. I got out of my car, I walked out to the observing field. I was on a little bluff and I looked down. And what I saw to my inexperienced, ignorant eyes, those cannons that they shoot people out of at the circus? That's honestly what I thought I was seeing. And I'm thinking, WTF, why am I seeing circus cannons? Of course, they were Dobbs. I queued up at a Dobb. Somebody much like some of you and me were running the Dobb. They were looking at M42. I was all excited. Finally, I get to look through a telescope. They were excited to describe what I was going to see. And I got up and looked through, and maybe you can anticipate what I'm about to say. It was a smudge. It was nothing. I was really disappointed. But I'll tell you, and the point of my story is, even today, I'll go back and look at M42. Why would I do that? Well, if it's a smudge, well, first of all, of course, our telescopes are better. We're going to dark sky sites. And also, we're much better at averted vision now, right? We can use our peripheral vision because we know how to use the more sensitive parts of our eyes. But all kidding aside, and you all know what I'm about to say. You've experienced this yourselves. And that is, when you come to the eyepiece, the more knowledge you have about what you're looking at, the more interesting and deeper experience it is. And that's I'm not going to keep dinging that. Maybe I'll wave this around. That deepening of my understanding of the entire field that spectroscopy brought to me really has made a difference. And this is an example, as I said, of a slit spectrometer. So up at the top there, we have some spectra. You can see some gaps there. There is the intensity graph of that feature. That's not a line, right? That's one of those forest of lines or band. We heard earlier that we see bands on cool stars. And similarly, these are certainly cool objects that can sustain and allow more complex molecules not to be burnt up. Well, what kind of complex molecule would we see on Neptune and Uranus or Uranus? Well, I'm thinking of a cartoon, which I'm going to have to add to this, that I saw online the other week. That was my laugh, as well as my perhaps mispronunciation. So we're seeing the methane atmosphere on these planets. It's amazing we can do that with just a backyard telescope. In fact, this is the same guy, there it is, Torsten Hansen, with just a imaging source video camera. So in 1881, Henry Draper, that's the Draper catalog guy, observed a comet, and the New York Times
thought it important enough to publish a report of it. Heck, if Hank can do it, so can we. Down in the lower left there, you can see there's the spectrum, the string of gems. There you can see these swan bands, mostly carbon. This was captured by a guy, Vikrant Agnihotri. He's a nuclear power plant engineer in Northwest India, Rajasthan. In 2013, he was a beginner. And, I was mentoring him and, helping him get started. Now he's an expert and I learned from him. And what teacher doesn't like to see their student charge on ahead and then learn from them? And I do, like I said, I do a lot of hand holding, and I don't say that in a disparaging way, a lot of helping, tutoring, mentoring of not only high school students, but also older people who are getting started and want help. So you're not on your own with all this. So here's a more contemporary example, NEO-WISE. Again, right down here, we can see the sodium that's visible in this yellow here. This was done with an objective grading, which is when you just, and I still can't find it, but you just screw an adapter. Well, here's one that's not anodized. You just screw a thread adapter onto the lens cap threads of a DSLR. And in certain circumstances, even with a low, small aperture, these can be really good spectra, sometimes better than what you can capture with a larger telescope. And why? Well, for a couple reasons. First of all, the star goes through the grating as parallel. The starlight is parallel as opposed to being in a collimated beam. That's the primary reason. So anybody who uses a C-clamp as part of their setup, that's my kind of guy, right? The problem is I break everything. So if I was using this setup, I would have torqued that C-clamp down and collapsed that camera housing. He didn't. This is captured by, or the setup is by Robin Leadbeater, who designed the star analyzer and then mounted it on the nose piece of a video camera. He looked at the Perseids, and here's a single frame that a Perseid traveled that distance in. So this is the actual zero order, it's called, or the star or the meteor. And this is the spectrum here, and that gap is that dip right there. And so he was, again, able to identify some of the composition. Different meteors have different lines, different features like this. This is a really esoteric kind of amateur astronomical spectroscopy, but, whatever floats your boat. It's sort of cool, but, you don't have a meteor every night that you can observe. So it's a little bit more challenging. So we're not going to talk a lot about the sun. We heard a lot about it a couple of years ago, and we're going to hear more about it in the next several years. Except to point out that this yellow feature here in 1868, when they observed the sun during a total eclipse, so it was just this compact object, because I don't think they had slit spectrometers back then. They didn't. So they saw that and they went, 10 years ago when Bunsen was burning everything and creating these catalogs, we never found something that was yellow. He didn't burn anything that burned that particular color, like at 5800. They went, we don't know what it is, but let's give it a name so we can talk about it. The Greek word for helios, for the sun is helios, we'll call it helium. Now you fast forward, many of you may know this story, you fast forward 40 years, a couple of researchers had some gas that they were trying to identify. They burned it, they looked at the spectrum, and they found that same yellow line. And they were able to say, Eureka, that stuff that we discovered on the sun 40 plus years ago and knew a physical feature and named it, we've now found here on Earth. I love this example because it so clearly shows how science works and how spectroscopy can serve us studying distant objects. Sort of cool, huh? If you're into novae, some have iron absorption features, others don't, even with a DSLR. Quick review of Doppler shift. If a car goes by you with its horn on, it's going to go from high pitch to low pitch, right? High when it's coming towards you, low when it's going away. Same thing with starlight. Before I tell you starlight, here's a cool way you can observe what I just described with a car. Next time you're out in the car, roll down the window and listen to the hissing sound as cars go past you the other direction, or parked cars, if you're going fast enough, or trees, they'll go high to low. I can't whisper those words, but okay, now back to the topic at hand. This triplet here, if we were expecting to see it right there, those three lines, and instead when we observed an object, we saw they were shoved over to the right, we would know that object is moving away from us and we were observing Doppler shift, presumably. That's redshift. If the feature, on the other hand, was shoved, and I use that word deliberately, shoved, it's totally non-scientific. I don't want to use the word shifted because early on when I was showing you this, for those of you who weren't familiar with this, shifted sort of gives away where I'm going. So if they're shoved to the left, another non-scientific term, towards the blue, the object's coming towards us. Okay, let's look at a quick example. There are different types of supernovae. I'm not going to get into a lot of detail. One particular type is called a type 1a. There's other types where a star runs out of fuel, collapses on itself, and explodes. But a type 1a involves two stars, and they're orbiting each other, and some of the gas on the bigger star ends up on the smaller star. And when you pour gas on a hot surface, what happens? You get an explosion. Okay, here's a really cool example. M101, there is a supernova. There's a photograph of another type 1a supernova like this one. It's a much closer supernova to us, so we were able to see that structure. Notice it sort of looks like it has it's like a sphere, maybe an exploding sphere. Well, David Strange in the UK captured this spectrum with a C9 and less than 15 minutes worth of integrating time. There's what the profile looks like, and see that deep dip? You see that dimming there? Notice how nice the dip shows it. So here's the deal. You know, we use that expression, we're standing on the shoulders of giants, maybe too much. In this case, hopefully not too much, but it's important to understand that we are building on just these geniuses of the past couple centuries. And they figured out that different supernova types, core collapse versus binary system, have different spectral fingerprints. And this is a pretty deep dip here, right around 6,000. Now, this next slide, this isn't going to be on the quiz, but a type 1a supernova has a really deep dip right around 6,000. And it's silicon. Notice these other supernovae, like this type 2, doesn't have a deep dip there, but has this really strong emission line. Again, I use the word dip because it's a little bit more self-descriptive than absorption line, perhaps. So this is one way that the professionals, this is the way professionals identify supernovae. One way, there's another one. And it's a way that we can help. And that is, there are a fair number of supernovas that need classification. And we can do it, and it gets done with a low resolution spectrometer like the Star Analyzer. There's lists of them. Tim Puckett gave a talk at a SAS conference in LA a few years ago and put up this huge spreadsheet of, you know, all these supernovae that need identification. That's the good news, and we can help out. The bad news is that they're not all that bright. They're all most often, unfortunately, in other galaxies. But it is something that amateurs participate in. Oftentimes there will be on some of our forums a call for observations, you know, new supernova, need classification data. Some of you may be familiar with, where is it? I lost this photograph. Let me find it. Give me a second here. I don't know where it is, but yeah, well, it's not there. But what I wanted to, I've been tweaking my show and it looks like I lost a photo, but I had a photograph here of Adam Rees. His team, just before the turn of the century, were using supernovae to observe the accelerating cosmological expansion of the universe. They won the Nobel Prize in 2011, and somehow I don't think they used this piece of equipment, but we can duplicate some of the work they did. Now, this is something new for me. I've given this talk a lot, but tonight's the first night I've used this. We talk in astronomy a lot about different ratios, signal to noise ratio. Well, I've got a new ratio that I want to apply here. You've used it before, probably. The bang for your buck ratio. Now, I can tell you this value, that's $200 for a grating. The bang, I don't know how we measure it, how we quantify bang. We're not talking about supernova bang, we're talking about the bang of excitement. Now, Adam Rees used telescopes, you know, $1 million telescopes, and we're down at $200. So anyway, just a little bit of fooling around there, again, to make a point that we can do neat things without a lot of sophistication. Here's some cool math real quickly. We're going to finish up really shortly here. And that is this dip, David and I measured to be at about 6,150 angstroms. Let's put that number up here. Now, we looked up on the web where if we were to burn silicon, or if say Bunsen had burnt sand, beach sand, he would have seen a line a little bit to the right at that wavelength. Now, the difference between those is due to Doppler shift. Listen, I don't know the Doppler shift formula. Even now, having given this talk many times, I could probably stumble through it, but Wikipedia helped. When we plug these numbers in, we were able to calculate the blue shift and thus the speed of that supernova shell expanding towards us. That's a big number. That's one wow. We should have another wow here for, wow, I did that with a 9-inch SCT in less than 15 minutes worth of integrating time. It's amazing, really. Now, the images I'm showing you tonight and these examples, these aren't like the creme de la creme examples, like the ones we see in the back of the magazines in the showcases. You look at those and they're just absolutely gorgeous images. They really, before I knew what I was doing, and I barely do now, before I was familiar with things, I look at those images and I wanted to do some of that. And then you read the fine print on the captions and it's like 25 hours worth of integrating time. Listen, I live in Seattle in the Pacific Northwest. Sometimes I don't get 25 hours worth of imaging time in a summer, you know, on a cloudy summer. It's so cloudy here. So, but the point I want to make here is these aren't those kinds of images. These are images that rank and file amateurs like you are able to capture. There, now it comes up. There's Adam Rees. So what about the spectrum of a black hole? Well, of course, a black hole doesn't emit light, but the accretion disk around it is. It's hot matter that's spiraling in and it glows. So David Strange down in Portland, Oregon, captured 3C273. And he captured the spectrum, which is over there. You can see two little points of light at those arrowheads. Let's blow that up. There they are. And there's the spectrum. So this guy, Martin Schmidt, was in his mid-20s in the early 1960s. He was looking at this, trying to figure out what are these peaks, these emission lines. And he was really frustrated. He decided, okay, I'm going to go back to square one. So a lot of times in science, as you know, we eliminate things that our subject can't be. So he said, first off, since hydrogen is so common, I'm just going to eliminate the possibility of these being hydrogen lines. So he brought up a hydrogen reference. This is that screen from my software I asked you to keep in your mind's eye. Not that this is Vega, but that these reference lines, hydrogen alpha, hydrogen beta, hydrogen gamma, but look, they don't really line up with our data up here at all, do they? So Martin Schmidt was able to conclude, well, these peaks here aren't hydrogen. That's a big step. Except they were, and he figured it out. They were massively redshifted. And using the Hubble constant, he and we are able to calculate the redshift as well as the distance of this object. That's a long way away. So the amazing thing, this was done, by the way, this was done with a modified security camera. We're not talking some expensive cooled camera here. So this light, think about how old this light is. And oh, I know, there were two things before I get into that. I know one of the things that delight a lot of us is, of course, just the enormous macrocosmic scale of the things we look at. And I've got two examples, forgive me, you may have seen these before. First of all, for this quasar to be so bright when it's that far away, it has to be brighter than 100 times all of the stars in the Milky Way galaxy combined. That's one number. That's pretty bright. And here's the other one that I really like. So again, these are all sort of subjective, sort of soft, appreciative kinds of things. If it was as distant as Pollux, and Pollux is, you know, pretty far away, like all the stars, it would be nearly as bright as our sun. That's a bright object. So what's remarkable is that this light came that distance over such a long period of time, and it still has information in it that we can tease out using such simple equipment. That light as if doesn't seem to age. Other things don't age as well. Most of us, for example, here's Martin Schmidt a few years ago. Now, listen, I I've been justly accused of throwing stones in in a glass house. Look, he's got a full head of hair I don't. I'm envious of the guy. Give me that at least. So 2 other examples and we're done. So the first one is, normally, so far we've been looking at things at about this resolution. We can see hydrogen alpha, beta, and so forth. Suppose we wanted to look at the detail of that hydrogen alpha feature. Wouldn't it be great if we could just roll our mouse wheel and zoom in on that? But most of us have done that with the moon. We go, hey, I want to see those craters more clearly, and you put in more magnification. Eventually you realize, I'm just not seeing anything more clearly. It's bigger, but it's not any more clear. There's no more information there. Same thing here. To get the details of these objects, the sub-angstrom details, we need to use one of those slit spectrometers again. I wanted to show you 2 brilliant examples of the way they get used. There's Vega with a slit spectrometer, and you can see there's lots of features there. Now, one of the other ways we do science sometimes is we compare a known with an unknown. So let's superimpose on this the spectrum of the moon, the reflected sun on the moon. Now, the moon isn't really moving towards or away from us appreciably. Let's see what that looks like. Well, look, the moon's hydrogen alpha is offset from the hydrogen alpha of Vega. That's from Doppler shift. Now, it's a really small amount of shift, 0.67, so we'd never, on this scale, be able to observe it. But we can use that to calculate the radial velocity of stars. So one final example here, and that is, this is a rotating star. This edge is coming towards you. This edge is moving away from you. First, there's Vega. And here's another way of saying what I just said. And that is, this star is rotating. This edge is coming towards you, so the light's blue shifted. This edge is moving away from you. It's red shifted. What would a spectrum of a star that was rotating really fast look like? Well, some of the light here would be stolen and over here. And some of the light here would be stolen over here, red shifted and blue shifted. That's what Altair looks like with a slit spectrometer. Notice that it's broadened and shorter because some of the energy has been stolen from the center peak. So the giants before us, these men and women really were just brilliant. Who would think, I certainly wouldn't, who would think that you could learn so much about the stars just by splitting the starlight? It's an amazing, amazing field. So how do you get started? Well, you need a grating. And I've mentioned that already. You need almost any sort of camera, DSLR, cooled fits, video, whatever. You need some software. I've been showing you that the whole way through. My software, if I was a better marketer, I would have said my software's name once or twice. RSpec stands for real-time spectroscopy, because with a video camera, you can in real time see that spectra, like I showed you in the outreach, the live Vega that you might use in a school. These are the software programs that I used 10 years ago that I described. I'm friends with the authors now. In fact, the 3 of us and some others have given several presentations to the AVSO. In August, it was to 400 people. And in just 2 weeks ago, it was to about 100 people, a workshop for the AVSO. I met them in France at a star party. In fact, when things open up again, it's a spectroscopy star party in Provence in southern France. So listen, being gender neutral here, whoever your spouse or partner is, if you have one, or friend, if you want a get out of jail free card, take them to southern France. Fields of lavender, it's gorgeous. You stay in a little village if you want, you sip wine, you have fresh croissants, and you're surrounded by people doing this kind of stuff. So I met them there, and they're great people, really great people. The software is really powerful. Still, a little rough around the edges. So the final thing you might need, this distance here, it's not like focus that it has to be perfect, but you don't want the spectrum too close, or this grating too close or too far away, because you don't want the spectrum to be able to spread out too much or not enough. So there's a calculator on my site where you enter your telescope information, your camera information, and then we're looking over here for some green flags. A lot of people just send me their specs using this link, and I figure it out for them. I tell them, oh, you need a little $10 spacer, or you need a different grating that we have, that kind of thing. It's pretty easy. There are lots of great books. This is a really cool one. On my site under links is a write-up of a really cool book, this Richard Walker Atlas. And there's a sample page from it. And you can see he's just calling out all the different features that you'd see. So it makes it really easy to at least find things and know what you're seeing. But knuckle dragging programmer that I am, I don't know the significance of nitrogen or this oxygen. So the great thing about this book is that he's got lots of text to go along with, I don't know if you can see that, to go along with these images. And it's aimed at us. It's aimed at amateur astronomers, not postdocs or PhD candidates. Great tool. And there's lots of other books too on my site. Just a side story. Most of you know that if you're an Amazon affiliate, which is free, and you link somebody and they follow that link and buy that product, you get a finder's fee or a commission. And legally, and my site now says that you have to say, you know, I get a little kickback. I make about $30 a year on book referrals. But here's the interesting fact that you may not know. I make money on anything that somebody buys if they go to Amazon with my link. So I've made 30 cents on a My Little Pony, a pink My Little Pony that people have bought for their kids. So it's just a little side story. We've got a great forum, lots of experts who know far more than I do, like helping people. The software is free for 30 days. In about 3-4 years ago, I taught a workshop to the AVSO in LA at that SAS conference. It was everybody had my sample data and they had their laptops, and we recorded it. And it's available. You can download my software. You can do this tomorrow morning. Download my software, download the sample data from here on the site, and then watch that YouTube video, hopefully on a second monitor. Even if you never were going to do spectroscopy, after a couple hours, you would have spectroscopy in your bones, and you'd really appreciate how easy it is to do and just how powerful it is. There are pro-am collaborations. These are all amateurs on this row. There aren't as many as we'd like. They're studying, and I'll tell you everything I know about this study. They're studying BE stars. They're type B stars. The E stands for emission. They're hotter stars. They have a circumstellar disk of dust that glows, and amateurs are helping professionals study these objects. So the AVSO has really jumped with Stella Kafka, their current executive director, and Arnie in the past, both professionals. They understand the importance in the field of spectroscopy and how it can really help the AVSO with its charter. So there are opportunities, more coming, as they just brought an online database up to speed recently. It's now online. You can submit data to it. So we're starting to see movement in that direction. So in the last 55 minutes, I ran a little longer than I wanted to. We've come a long way. I know, as I mentioned earlier, it sort of feels like drinking from a fire hose. I apologize for that. Also in the 200 or 300 past years, we've come a long way. Just from knowing nothing, we can now understand a lot about the stars. We may not be able to touch them, but we get pretty close to understanding them. I'd like to thank the club for inviting me tonight. It's a dynamite club, has a great reputation, and I understand why. Hopefully you smiled at some of my jokes, either at the jokes or at me telling them. Either way, it's fine. If I get a smile, I suppose it releases some sort of dopamine or something and primes you for being a little more wide awake. I love answering questions. I'm happy to answer any that came up tonight. There's a contact form on the site. You can send me email. Feel free to badger me to answer questions. So with that, I'll stop screen sharing, and we can handle whatever Q&A questions came. There's one. And the question is from Dean, and that is, does my software work with nonlinear dispersion of the prism? See, just to explain that question, when this spreads the starlight out, it spreads it out in a linear manner, meaning that the red is shifted proportionally the same amount as the blue. And the answer Dean is looking for is, he's using a prism, and a prism doesn't do that. In fact, quite a few spectrometers don't. It's nonlinear, and yes, that is, you're welcome, Derek. That is, the software does, just like all the software that's out there, it allows you to do a polynomial fit and calibrate a nonlinear spectrum. Although the examples I showed in the software tonight were just with the grading here, it also handles standard slit grading or slit instrument spectra and you bring your calibration tube data image into the same screen and then superimpose the two and go about the calibration process. That's a good question. Are there any other questions? I see some were answered there. It doesn't look like they're for me.
There's
But,
one in the chat, Tom.
Oh, okay. Let me
About
pop that up
8-inch
here.
Dob.
There we go. And I don't know if I scroll to the bottom. Oh, there, bottom. Tom, makes sense. A lot of clouds. Nope. Where is it? Fantastic. Oh, can you do it with an 8-inch manual Dob from Janet? Yes. And there is a 20-year-old woman named Lauren who gave a presentation at the AVSO 10 days ago. And she's doing it with a Dob. If you have tracking, it's a lot easier. If you don't have tracking, she's figured out a way. If you orient the grading so that the spectrum drifts vertically, since we're summing the columns anyway, that's fine. It's not smeared. We get the same data. And so there is a way to do it with Dobs, tracked or not tracked. The key to that would be on my site, and I just want to share it for, well, I don't need to. On my site is that calculator where you would apply, your telescope's focal ratio and aperture and your camera size and stuff, and it'll tell you whether the grading is optimal for your particular setup. It's a great question. How critical is focus, and will autofocus be possible? Great question, Leo. And no, focus is critical, and autofocus is not possible. And that's because the proper focus for the spectrum is not the same as the proper focus for the star. And I'm going to try and hold this up and see if you can see it. I guess you can. So there's the starlight coming through. So that's your distance you're focusing on with the star. Notice that the colored spectrum those colors are traveling a different distance. They're not coming straight down. So the trick is focus on the star and then change your focus a little bit. The good news is the amount of defocus is the same for every star you look at. So once you figured it out, if you have a way of recording that, you don't have any problem focusing in the future. There's a getting started manual on our site. I can send you a link to it if you can't find it, that talks about focusing. There are some tricks to focusing, but it is somewhat important. For visual, you want to gather more light for Orion, not magnification. Use around 40 millimeters for that. Okay, good. Thank you. Other questions?
Q&A has a couple that populated.
Where are these? Oh, in the Q&A, thanks.
Yeah.
2-inch grading, is a 2-inch grading better than 1.25 inch? We all have aperture envy. And yes, a 2-inch grading is better. But, I had a friend, I used to have this slide in my talk, a friend, he lived in LA in the 70s. He worked on Porsches. He was a car mechanic. They had a sign on the wall of the sales room for Porsches, high-end cars. And the sign said, and it applies to telescopes just like it applies to cars. And it said, speed costs money. How fast do you want to go? And the deal is that 2-inch gradings have to be custom made. And just like chips, there's defect rates and things like that. A lot of people will use just a step down for their 2-inch telescope mounts for the 1.25 grading. Again, you get great data. 2-inch grading would be great. You can get them custom made. They're like $600 or $700. Video cameras. Can you use a simple HD video camera? Not all that well. Part of the problem is, just finding a way to attach the grading to the nose piece of the camera. I mean, you're not going to have a nose piece with the 1.25 threads on it. Good cameras, again, it all depends on how deep your pockets are. The ZWO cameras are great cameras, as a lot of you know. And this is a color camera, so it's not as sensitive as I mentioned. This is a 178. So it works well. It's mid-range price. I think it's what, $300 or something like that. The key with cameras is you need to know, unless you're willing to experiment, which could be fun if you're into it, you need to know the pixel size of the camera and how far back the sensor is from where you're going to attach the grading. I can help you with some of that. Online research sometimes helps. You might be able to put an HD camera together. One of the keys would be be able to turn off all the automatic exposure controls in that camera. you know, our most AV cameras for, you know, personal use, they have all sorts of automatic exposure control. So the images are pleasing. They're not too green. They're not too red, right? Color balanced, all that. We don't want any of that. We want, and nor do we really want the Bayer filter that comes with them. You can, as I said, use color cameras, but they're not the best. Anyway, other questions? Is that it? It looks like I don't see any numbers there. So it looks like I'm going to be able to go upstairs and get dinner.
Yeah, I think you.
Oh yeah, I was going to mention, Tom mentioned, and I forgot. Oh, and he said it right to me. Thank you, Tom, for the prompt, and he's right. You have some members in the club. I know I got an email from Woody Sims tonight. He actually ran one of those AAVSO workshops, and he's really at the top of the game in terms of spectroscopy. He's very humble because he knows how much there is to learn if you really want to go deep. He organizes meetings of amateurs doing this kind of thing. Great guy. I've met him at a couple of these conferences. I consider him a friend. Bob also. Bob, I don't know how to pronounce his last name. Buchheim. Is that how you pronounce it, Gordon? Buchheim? Maybe you'll see.
Yeah, I'm not sure.
Anyway, so he's, sorry to put you on the spot like that. He's done some nice mentoring in the past. Some of you club members may know him, and this is an opportunity before I let you go, if I can find it. He has a great book. He's got several great books. If you're into this kind of stuff, this is a really wonderful book by him. It has all sorts of really interesting projects to do and to read about. So he's a good guy. And also Wayne Thomas is also a great spectroscoper. These people have been doing it for years. So you have some good resources there as well as with me. Anyway, I would like to thank you again for those of you who do outreach. I'd like to especially thank you. I think it's the way, as you know, it's fun, but I think it's also the way that we pay it forward and we pay it backward for the opportunities we've had and been able to take advantage of. We know we took advantage of them because we're here tonight. So thank you again. And I'll leave and let you all talk about me behind. Oh, it's a webinar. You can't do that. But anyway, thank you all for everything you've done and for inviting me tonight.
Oh, thank you, Tom. And we did enjoy your humor. That
good, thanks.
Was appreciated. And I'll turn it over to Gordon. Let Gordon close us out.
Yeah. Okay, guys. This is can you hear me okay and see me okay?
Yeah.
Participants, this is a great example of what our club is still doing during these basically awful times. And I would just want to thank Tom Field for joining us and being a part of this. I saw a presentation he did a few months back, and when I found out that Tom Mosden could get him lined up for ours, ecstatic about it. And I'm sure that everyone else like me, I'm so jazzed up from his energy and his humor that I think I'm going to have to go run around the block a few times to calm down. But it's a very good example of what our club is bringing to its members and guests also. So think about joining the club and keeping this going. We're financially pretty solid right now because we still have bills to pay. We have insurance, we have fees for the internet. We do some donating like to the International Dark Sky Foundation, things like that. So we still have some outflow, but we're still doing financially pretty solid. But for next year, we need your membership renewals. So start thinking about doing that. And we'll push that next December and January. So remember, y'all, there's a special presentation coming up 5th of December as we celebrate how everybody has been supporting this online activity. 5th of December, it's a Saturday at 10 a.m. Our next meeting is back to the normal Fridays, third Friday of the month. It's on 18th of December. And again, 7:30, just as usual. So we had about 70 participants.
75, yeah.
75?
Yeah.
Okay. And Claude reported that our affirmation vote, we had 41 yeses and no no's. So our current officers are now our new officers. So congratulations to the new officers who are the same ones. But that's great, because we'll make sure that things continue on. So what I will do is give everyone a chance, last minute, last chat in. Tom, if you have anything.
I don't. I did notice our December speaker, Ed Bowie. He attended the meeting. He just signed off, but
Okay.
that'll be a good talk. Anyway, Dan, I'll thank Tom Plakas for suggesting Tom Field. The VP is always interested in getting suggestions from anyone. So if you have a favorite speaker or a topic you want, send me a note. I'll see what I can do.
All right. Thanks, y'all. And I will give the usual countdown and we'll sign off. So 3, 2, 1. So long, everybody. Thanks for joining in.